The third gas law is called Gay-Lussac's law, which describes the everyday experience of heating a gas in a closed container. If we heat a gas stored in a closed container, its pressure builds up, that is, we increase the pressure of the gas in the container. In the photo we can see the failure of a high-pressure vessel in hydrostatic testing, but we may have a similar result if we heat a great amount of gas in a small container with thin walls. The quantitative description of this effect is simply that the change in the temperature of a gas confined to a constant volume changes its pressure. This effect was studied systematically by Guillaume Amontons in 1699. Since he used Torricelli-type barometers shown in the figure from his publication, the results of his experiments could not be very accurate, and his analysis was at best semi-quantitative. Nevertheless, he could demonstrate that the pressure of a gas increases by roughly 1/3 between 0 and 100 Celsius. His results also helped him to anticipate absolute zero, when he speculated about that a sufficient drop in the temperature may lead to the vanishing pressure of a gas. Joseph-Louis Gay-Lussac could perform more accurate measurements in 1802, when he studied the relationship between the temperature and the pressure of a gas confined in a container. The picture shows the apparatus used in his experiments. He was the first one who formulated the third gas law, stating that the pressure of the given amount of gas increases linearly as the temperature of the gas rises, provided the volume of the gas is held constant. As mentioned before, he also demonstrated the second gas law, when he found that the volume of a given amount of gas measured at 0 degrees Celsius has an expansion by a factor of 1.37 at 100 degrees Celsius. In fact, we can perform the same experiment with some modifications to establish both the second and the third gas laws. Therefore, we use the apparatus presented in the demonstration of Charles's law, to study the change in the pressure of a gas while we heat the gas and keep its volume constant. The apparatus consists of a piston in a cylinder and a manometer, which are connected to a container filled with a gas. Both the cylinder and the manometer are filled with mercury, which seals the gas in the container. The heights of mercury columns in the manometer and the glass tube leading to the container can be controlled by moving the piston. Let us suppose that the gas is extended to the height A1 in the glass tube for the initial temperature T1 and volume V1 of the gas in the container. The height A1 determines the total volume of the gas sealed by the mercury column. The pressure of the gas in the container also determines the height B1 of the mercury column in the manometer. The difference H1 of the heights B1 and A1 is proportional to the difference between the atmospheric pressure and the pressure of the gas. By heating the gas in the container, the temperature of the gas can be raised from the initial temperature T1 to a given temperature T2. The gas will expand and its volume increases to the volume V2. Since the expanding gas displaces some amount of mercury in the glass tube, the height of the mercury column drops to the level A2. At the same time, this amount of mercury fills the manometer, and the height of the mercury column raises to the level B2. We can compress the gas in the container if we pump more mercury into the glass tubes by moving the piston downward in the cylinder. In the final state of the system, the height of the mercury column in the glass tube is increased to the level A3, and the height measured in the manometer is equal to B3. If we pump such an amount of mercury into the glass tube so that the height A1 is equal to the height A3, then we have restored the initial volume V1 of the gas in the container, whereas the temperature of the gas has remained T2. Here H3 is the difference between the length B3 and A3, which is not equal to H1. That is, the difference between the atmospheric pressure and the pressure of the gas in the container is not the same in the initial and the final states. However, the volume of the gas is the same in the initial and the final states, and we can talk about the heating of the gas while its volume is held constant. The initial and the final temperatures of the gas are T1 and T2, respectively. We only need to calculate the increase in the pressure of the gas during heating. The height of the mercury column in the manometer measures the pressure in millimeters of mercury. Therefore, the increase delta P in the pressure of the gas is equal to the difference of the heights H3 and H1, which is measured in millimeters of mercury. If we perform this experiment with different pairs of initial and final temperatures of the gas in the container and measure the increase in the pressure of the gas for each pair, then we can compile a table from the data and study the relationship between the change of the temperature and the change of pressure of a gas. In order to achieve a precise measurement, we need to apply some corrections for the thermal expansion of the container and the different gas temperature in the glass tube connecting the manometer and the container. This method was applied by Gay-Lussac in 1802, who formulated the third gas law known as Gay-Lussac's law. Gay-Lussac's law states the following. If the volume of a gas is held constant, then the pressure of the gas is a linear function of the gas temperature. That is, the pressure P is equal to the reference pressure P0 times 1 plus beta prime times T. In other words, the ratio of the pressure change delta P to reference pressure P0 is equal to beta prime times T. The temperature T of the gas is measured in Celsius, as in the case of Charles's law. Here beta prime is called pressure coefficient, which is the same for all gases. That is, beta prime is a universal constant. It is equal to 1 over 273.15 Celsius, which is equal to 0.003661 per Celsius. P0 is the reference pressure, that is the pressure of the gas at 0 Celsius for a given volume. This formula tells us if we heat a gas closed in a constant volume from 0 Celsius to 1 Celsius, then its pressure P0 increases approximately by a factor of 1 over 273. We can also derive the general form of Gay-Lussac's law in the same way as in the case of Charles's law. The general formula states the following. For a constant volume, the pressure P of a gas measured at the temperature T is equal to a reference pressure P1 of the gas measured at the temperature T1, times 1 plus the ratio of T minus to T1 to 1 over beta prime plus T1. Here T1 is an arbitrary reference temperature. We can also substitute the value of the pressure coefficient in the equation. We see that the pressure coefficient is equal to the volumetric expansion coefficient, that is beta prime is equal to beta, and the expansion or contraction factor in Gay-Lussac's law is the same as the one in Charles's law. We have seen that the pressure coefficient is a universal constant, that is, beta prime is independent of the material properties of the gas. Therefore, Gay-Lussac's law is valid for an ideal gas without any restriction, just like Boyle's law and Charles's law. Or the other way around, the ideal gas is defined as the gaseous substance for which Gay-Lussac's law and the two first gas laws are valid. In the first two gas laws, we introduce the concepts isotherms and isobars. For the third gas law, we can define a third type functional relation between the physical properties of the ideal gas. This relation is represented by isochores, which are functional relations between the temperature and the pressure of an ideal gas for a constant volume. That is, we can express pressure as a function of temperature for a constant volume, when an ideal gas undergoes an isochoric process. Or we can determine its inverse function, in which we express temperature as a function of pressure for a constant volume. From Gay-Lussac's law we see that isochores are lines in the temperature versus pressure plot for a given reference pressure P0 of the gas with a constant volume. The tangent of an isochore depends on the reference pressure P0, that is the ratio of delta P to the temperature T is equal to the pressure coefficient beta primes times the initial pressure P0. Therefore, another reference pressure P0 prime gives another isochore with a different tangent. We also see that Gay-Lussac's law, which describes the change in the state of a gas undergone an isochoric process, does not have any explicit dependence on volume. In fact, we can combine the three gas laws into one gas law, which describes an explicit functional dependence between the temperature, the pressure, and the volume of an ideal gas.